Hello students, I am Dr. Krupa Rasane, Professor and Head ENC, Jain College of Engineering, Belgavi. Today we'll be looking into the 7th module of Power Electronics, BE 7th semester ENC Engineering.
Electronics 7
The
semester.
textbook referred is
So in
Mohammad
module
JCE
4 we are
Power
basically
Electronic
dealing
Circuit
with DC
Devices
to DC
and
chopper.
Applications.
So coming to the
In this
content, we
particular
have been
video, we'll be
looking
looking
into the
into the
step up
converter
chopper, the
classification. We have
step down
already
chopper
seen the
with R and
classes of
RL load. We have also seen certain
converter
examples
of DC to DC
with respect to
converter,
the
that is
chopper,
chopper,
example
with
problems
respect to the
and
quadrantal
performance
operation.
parameters
In
we
this
have
video,
seen.
we'll be
And
looking
now let
into
us
the
move on to the
other
converter
types of
classification.
chopper classifications known as the switch mode regulators, in which we have got basically 4 types: buck regulator, buck boost regulator, Kirk regulator, and then we have the chopper design circuit. Today we'll be looking into the buck regulator. So switching mode regulators. So what are switching mode regulators? Basically, switching mode converters or SMPCs. They consist of switches for control of power flow and reactive circuit elements, which consist of inductors and capacitors, and for attenuating the switching ripple low pass functions in the DC output. So we know that whenever we are converting DC to DC, at that the output you are going to have the currents which will produce are in the ripple format. And if we have to reduce these ripples, we have to use the filtering elements such as inductors and capacitors. The output voltage of a real converter will also depend on the non-idealities in the converter, such as the switching voltage drop, etc. Right? So these drops, though we say the switches are ideal, they are not always ideal. There will be certain voltage drop that will come across the switch itself, and that may reduce the output voltage further. As a result, SMPC operating with a fixed duty cycle, that is open loop control, will not be able to maintain the output voltage of the converter fixed. So what we saw was the input, we had a chopper and we had an output, right? So this is an open loop. So we say that I'm just controlling the on and off time of the chopper, but sometimes the output load voltage will vary depending upon the fluctuations in the input as well as the load terminals. So we cannot say this is an open loop control, and we cannot say that the output voltage can remain stable because of all these parameters. Therefore, it is essential that SMPC be controlled in a closed loop with appropriate feedback to regulate the output voltage of the SMPC. So in all the, we saw the quadrantal operations, there was not an element of any feedback from the load to the, controlling element or chopper. But here we are going to provide a feedback which is going to regulate the pulse width so that the output voltage will remain fixed. So the purpose of this chapter is to consider the SMPC as a system and develop an appropriate dynamic model for the converter. So what is the significance of this DC to DC converter? Let's consider electronic switch mode converters used in cell phones, right? And also the laptop computers. These devices are powered using rechargeable batteries. These batteries has the power all the components in the cellular phone or laptop, such as display, USB devices. So many components are there inside these particular devices. Each of these components may be operating at different voltages and current levels, obviously. So DC to DC converters step up or step down DC voltage level so that it will be suited to the requirement of an interest. So this is the typical block diagram of a switch mode DC to DC converter. What you are going to observe here would be an input voltage as we have seen in a normal chopper, and we have got the output voltage. So this is basically converting DC to DC with respect to the chopper, DC chopper. Okay. Now this chopper is being controlled with the on-off control. We know that how chopper works, right? And output is basically a function of the duty cycle of the chopping frequency. So that is how we are doing. That is, we are producing the duty cycle or on time and off time, and that is being given to the DC chopper, right? But in SMPS, we are going to provide this additional thing, that is the feedback. So in the feedback, the output is always sensed. Okay, a part of the output is sensed, you can say, and it is compared with a reference voltage, which is internally. Now, this reference voltage will not change, it is always fixed. And whenever this output changes with respect to either goes above the reference or below the reference, an error voltage will be generated. And this error voltage will be magnified, and that actually controls how should be the on time. Means if the error is positive, that means the output is more, so we can reduce the on time. Likewise, we can control the output voltage with a feedback system. So these are basically the elements of switch mode power supply. So we'll have an input DC, we'll have an output DC, we'll have a chopper which is being controlled by a controlling circuit, which in turn is basically controlled by a feedback system, okay, consisting of an error detector and an amplifier, and that will control and make sure that the chopper frequency or duty cycle is continuously changing, so that output will not be changed. So pulse width modulated converters. What do we understand by pulse width modulated? As I said, if I control the on time, if I increase or reduce the on time of the chopper, right? That means I am controlling the pulse width, keeping the frequency fixed. So that is basically, so if I want to increase, let's say the output has decreased, right? So if the output has decreased, maybe for any reason, I would like to increase the on time so that the output will come back to its original value. So how do I increase this on time? This on time can be increased by this DC line, which is actually being compared with this sawtooth waveform. So if I increase, sorry, in this case, I'll have to decrease the DC voltage, that is control voltage, we call it as VC. If I decrease it, you can see the pulse width is nothing but the intersection points of the chopping sawtooth waveform. So this is the point at which it will start to turn on, and this is the time when it will turn off. So turn off is always going to be fixed because this is a sawtooth. But turn on can be controlled by controlling this control voltage, DC voltage, by moving it up and down. So if I move it down, you can see the on time will automatically increase. And if I move it up, the on time will automatically decrease. So in this way, basically, we can control the pulse width modulation, and hence this is a pulse width modulated converter. Width gets modulated. Modulated means changed with respect to certain parameters. This is a simplified representation of SMPS. What we see is this is an BJT which is acting like the switching element of the chopper. We have got an operational amplifier, op amp here, right, whose output is controlling the base of the transistor. Now, this is an NPN transistor, right? So, if I give the base current, the transistor will turn on more. If I reduce the base current, the transistor will reduce. This here, what we are doing, we are giving the output. Output is having a capacitor which acts like a filtering element. And also we have got a resistance divider. So we'll not take the complete feedback of the output. We'll take a part of the feedback. So the voltage that is coming across R2 forms the reference voltage, or sorry, the feedback voltage being given to the negative of this op amp, and the positive of this op amp is being given by a zener which acts like the reference voltage. So this is always fixed, and this will change basically depending upon the output load conditions. So if it increases or decreases, it is always compared with the reference voltage, and likewise an error voltage will be generated, which in turn controls the base of this transistor, so which is controlling the power that is giving to this transistor to turn on or to have more current or less current that is flowing between the collector. So increase or decrease of this collector current base depends on the base. Base current basically depends upon the difference between these two voltages. So this is how your simple regulator works. This is a linear regulator, right? BJT is basically working on the strength of the current given to the base. More current to the base, more it is turning on. So we call it as a linear regulator. We are not turning it on and off, right? We are only controlling the amplification of that particular transistor. So unlike such linear regulators, switching converters, they use power semiconductor devices to operate either in the on state or off state, or the right. So because of that on state or off state, all we are doing is controlling how much is the width of the on state. So this is the basic difference between a linear, the previous slide was a linear regulator, and a switch mode regulator. The reason that when I operate a device in the on state and off state, the power consumption or power loss because of these switching elements will decrease drastically. Since either state will lead to a low switching voltage or low switching current, it is possible to convert the DC to DC with higher efficiency using a switching regulator. AC to DC power converters with multi-output applications. So compared to the linear block diagram, a switching network and high frequency output electrical isolation transformer T2 is also being added. So the objective is to control the on time of the power devices to regulate the DC output voltage. The post filtering is used to reduce the output voltage ripple. Of course, this is going to have a ripple at the output switching mode regulators, but then we can use filtering to reduce the ripples. So the basic circuit diagram, all fundamental converters are shown in the figure. I told you the first figure. They consist of the same basic elements. The building block of these converters are DC supply Vs, load, diode D, power supply, switches, inductors Ln, capacitor C. Now coming to the classification of converters. Okay. So based on this SMPS, let's see, we have the first one, that is the buck converter. Now the buck converter is a step down converter and produces a lower average output voltage than the DC input voltage. Boost converter. A boost converter is shown to have an output voltage which is greater than the input voltage. So this is like, buck is like step down and boost is like step up. Buck boost converter. A buck boost converter is also shown. We'll see them. The output voltage can either be of a higher value or lower compared to the input voltage. Now we have the chuck converter, sometimes called as, pronounced chuk. Okay. So this is the chuk converter and is a type of DC to DC converter that has an input voltage magnitude that is either greater than or less than the input voltage magnitude. So the buck boost converter and chuk converter, these are similar in terms of definition, but definitely there is a difference between these two converters. It is essential a boost converter followed by a buck converter with a capacitor to couple the energy. So we have seen these four types of converters are there. This is your simple buck converter. You can see it represents your simple step down chopper with a filtering element LNC and then given to the load. And in the boost also, this is like your step up transformer, step up chopper, and we have got the chopping frequency in parallel like this, and it is controlling the output voltage. And these are the basic simple converters, DC to DC converters, and of course we have not shown any feedback element out here. And this is your buck boost converter, right? So you can see here the difference here. I'm putting the switching element in series, so it acts like a step down chopper as well. and we have this inductor in parallel, and you can see the load can be feeding back, right? So the diode is basically used to carry the current in this direction, and in buck boost we can have the phenomenon of step up and step down. This is the Chuk converter, and you can see basically it is looking like a boost here, right? And we have the capacitor element in series, and this diode is coming down. So let us see how each of these basic circuit works to help you to give the required necessary output. So for the buck chopper, energy only goes to the load when the switch is closed. So that is the basic thing. In buck, it's a step down chopper, and energy always goes from the load when the switch is closed, right? Goes to the load from the supply, like this. For the boost chopper, the energy only goes to the load when the switch is open. So when this is open, then only the load will get the supply. When this is off, the current will circulate like this. It will not go to the load. So that is the two difference. In buck, energy goes to the load when the switch is closed, whereas here the energy goes to the load when the switch is open. With the Chu converter, energy is transferred when the switch opens and when it closes. So in the Chu converter, we are going to have the energy being transferred when the switch opens and when it closes as well. Okay. So we'll see the function one by one. But in this, we'll be looking only into the buck. Since these converters' function is to reproduce DC output, the output voltage consists of the desired DC and the undesired AC components. Practically, the output ripple due to switching is very small, which is less than 1% compared to the level of the linear DC output. As a result, we will assume the output ripple voltage is small and can be neglected when evaluating converter voltage gains, that is V0 is 1/4 of V0. That is, in other words, let's say it is ripple free. Now looking at this particular buck converter, please note the circuit diagram. We can explain them basically in two modes of operation. That is the switch on mode, that is when the switch is on. When the switch is on, you can see this part is closed, right? And you will be dealing with inductor, capacitor and the load as shown in this particular equivalent circuit. So this is mode 1, and we say this is when the switch is closed. This is obviously mode 2, and that happens when the switch is off. When the switch is off, the input supply gets disconnected from the load, and the current that is flowing will be in this fashion. This is IL, and this is IC, and this is I0, right? So the current of the inductor, or the stored energy in the inductor, will be dissipated to the capacitor and to the load, and this happens when this freewheeling diode comes into picture and making this inductor to discharge through the load without including the Vs. So two modes of operation. This is the circuit when switch is on. This is the circuit when switch is off. So in buck regulator, the average output voltage, we'll use it output voltage as VA, is less than the input voltage. It's a step down chopper, and hence the name buck. Buck means we bend, right? And this is a very popular regulator. The circuit operation can be divided into two modes, as I just told you. Mode 1 begins when transistor Q1 is switched on, that is, let's say at T equal to 0, and the input current will rise and flows through the filter elements L and filter capacitor C and the load R. The mode 2 begins when transistor Q1 is switched off, that is at T equal to T1. I'll show you the diagram. The freewheeling diode DM conducts due to the energy stored in the inductor, and the inductor current continues to flow through LC load and the freewheeling diode DM. The inductor current falls because it is discharging. The current will now fall until the transistor Q1 is switched on again. in the next cycle. So these are the two modes of operation that we have seen, and you can see that in the mode 1 operation you can see the waveform. So this is when t equal to 0, the switch is on and the switch is, input supply is connected, okay, to the load, and the current is basically flowing through the load, through the switch, and the current is increasing fashion. At t equal to t on, kt means t on, right? And 1 minus k into t means t off. Here, 1 minus k into t means, so this is off period and this is on period. So at this off period, we call this period as t1 and we call this as t2. So during t1, switch is on and it is mode 1 and the current is rising. During t off, the current will be falling, right? And this is your time period, capital T. So let us look at the currents that are being shown here. This is the supply current. The supply current will follow the load current till here, right? And then in mode 2, the supply current gets disconnected. So we can show it with this no current here till the T off is there. Then again, after some time, but small amount will be flowing continuously. You can say that is because of all the leakage currents and all that. And it is required also that small current keep circulating through the load. And after this period, again T on starts, so the current is going to increase. Now this is the collector current that is there. Now collector current will have the current IC value, right, which is equal to I2 minus IA. So whatever is flowing through the load will be subtracted, and the current, if I call this as I2, right, and this I call it as I1 here. This is I1 and I2, right? So that minus the load current will be the actual current that is flowing through the capacitor. So you'll note that the capacitor will be increasing, has both positive and negative values when it is charging or charging through the inductor, which is, and then again when in the mode 2 it is going to decrease, right, the current, and even go negative, because when it becomes 0 the inductor will not stop its current to become 0. It will continue to go in the negative direction in this till it reaches a on time, and then again it starts charging. This is the inductive effect that it will be there, right? And the capacitor will sense both the negative as well as positive directions of currents. Now this is the voltage across the capacitor, and if voltage across the capacitor, we can show that the current is, when it is increasing, it is going to have your capacitor voltage positive and negative. So this is how we can show the capacitor voltage, and the load voltage, I'm assuming it to be fixed always, a DC voltage. Okay, so the capacitor will always take away all the ripple that are there in the load voltage, and the load will only get the DC voltage. So this is your buck regulator. So two modes of operation, when the switch is on and when the switch is off. So understanding this with the equations, let's see the voltage across the inductor, right? So the inductor voltage, we generally give it as EL is equal to L into di by dt. Assuming that the inductor current rises linearly, from where it rises? It rises from I1 to I2, right? So di means di2 minus I1, dt means it is basically from 0 to T1. So it is T1 only. So the voltage across the inductor, because the switch is closed, it will be Vs minus the voltage across the load. So Vs minus Va, that is EL, is equal to L into I2 minus I1 by T1, and this can be represented as L into delta I by T1. Or we can take the T1 on the left hand side, and I will get an expression for T1 is equal to delta I into L upon Vs minus Va. So this is your T1 equation. And the current starts to fall linearly from I2 to I1 in the time period of T2, right? That is during the off time or mode 2. And the inductor current as it falls, we can say that minus VA. See the voltage. Now, in this case, the voltage is equal to the load voltage, that is minus VA is equal to L into minus L into di by dt. So what the voltage across the inductor will be, EL voltage will be now equal to the voltage that is at the load, because this is now closed. Vs is removed. So the voltage for it will be minus VL, because this terminal comes here, right? So then only the diode will conduct. So the voltage across the inductor is basically the load voltage. So it is minus VA, and that is equal to the minus L into di delta I by T2. So T2 becomes equal to delta I into L upon VA. So this is the voltage equation for T1, and this is T1, and this is for T2. Where delta I, we are assuming that delta I is again going from I2 to I1 in this case. It is peak to peak ripple current of the inductor L. And if I take delta I on both the sides on the left hand side and equate them, then I will get delta I equal to Vs minus VA into T1, right? Delta I equal to Vs minus VA into T1 upon L. So that becomes equal to VA into T2 divided by L. So this is an expression we are trying to, equate. Next, if I substitute T1 as the on time, that is KT, and T2 as the off time, that is 1 minus K into T, and substitute, I will get VA is equal to Vs, right, into T1 by T, which is equal to K into Vs. So this is a sort of definition or equation how to get an output voltage. So it is, we are getting an output voltage which is K into Vs. So what is K? K is nothing but the duty cycle. So output is equal to duty cycle into Vs. So assuming a lossless circuit, and hence the input power is equal to the output power. So we say that the circuit has no power loss, and hence input power is equal to the output power, and output power VA is nothing but K into Vs into IA, and the average input current IS, if I equate, it becomes IS becomes equal to K times IA, because this Vs and this Vs will cancel. Now let us look at the peak-to-peak inductor ripple current. The switching period T can be expressed as T, you know how it is always 1 by F, and this is equal to T1 plus T2. We know we have already derived T1 and T2. If I substitute the values of T1 and T2, I should be getting the T is equal to delta I into LVS upon VA into Vs minus VA. So this will give me, take the delta L on the I on the left hand side, that will give me the peak to peak ripple current, which is equal to this VA into Vs minus VA upon, okay, T is here, so that T becomes F1 by F into L into Vs. So this is the equation, the derivation for peak to peak inductor ripple current. So delta I is equal to Vs into K. If I substitute VA equal to K into Vs, Vs into K into, take it outside the bracket, it becomes 1 minus K upon Fs. Vs will get cancelled. So this is how I will get an expression for delta I. Remember, delta I is equal to Vs into K into 1 minus K. Just substitute for VA as K into Vs, and you will be getting this particular equation. Now let us look at the peak-to-peak capacitor ripple voltage. Okay. So using the KVL current law, we can write the inductor current IL is equal to, see, the inductor IL is equal to the capacitor current plus the load current. So we know that. So if we assume that the load ripple current, the change in the ripple current delta I is very small. I told you that current through the load I'm assuming as a perfect DC. So there is, we are assuming there is no ripple or very negligible ripple. I can say that the IL, delta IL, that is change, the ripple current or the load IL, the current through the inductor, ripple current is same as the current through the capacitor. The average capacitor current which flows for T1 by 2 plus T2 by 2 is equal to T by 2. When I take average, I'm going to divide it by 2. So I will get the current that is flowing through the capacitor as delta I by 4. Okay, so the average current flowing for the on time, the average current flowing by the off time. And since I'm taking average, I'm going to divide it by 2 here, divide it by 2 here. So delta IC, I can say that it is delta I by 4. The capacitor voltage is expressed as the capacitor voltage VC is equal to 1 upon C integrate IC DC plus VC at T equal to 0. And the peak-to-peak ripple voltage of the capacitor delta VC is equal to VC minus VC at T equal to 0. If I substitute this as equal to 1 by C integrated, so IC I will substitute as delta I by 4 into dt, and this will give me delta I into T by 8C, right? So this will be equal to delta I upon 8 FC. So integration of delta I is common, okay, and I'm going to substitute this T by 2 here for T, and I will be getting that as 8 FC below in the denominator. So we have an expression for IC here, and we have already derived the peak-to-peak ripple current, and now this is the voltage across the ripple voltage, right? Peak-to-peak capacitor voltage that we have just derived. So remember these formulas so we can use them in a problem. Now, here we have got delta I. Let us substitute delta I in this equation, and I should be getting the expression for delta VC as, okay, delta I we know is equal to VA into VS minus VA divided by, right, we have got, if I substitute, it becomes 8 LCF squared VS. So this is how we have got the expression for delta VC. Our delta VC can be simplified further, which gives you VS into K. Substitute VA as K into VS, and I'll be getting VS into K 1 minus K upon 8 LC F squared. So this is basically the summary of the buck regulator. The peak-to-peak ripple current is given as delta I equal to Vs into K 1 minus K by FL, and the peak-to-peak ripple voltage is given by delta Vc equal to Vsc. It is simple to remember. Both are Vs into K 1 minus K in the numerator. This is simple FL, whereas here it is 8 LCF squared. So if you can remember that, these are the two peak-to-peak values, electrical parameters across the capacitor. Now, condition for continuous inductor current and capacitor voltage. If IL is the average inductor current, now you can see this is the average of the inductor current, then the ripple current delta IL will be 2 times IL. Okay, this is what we are assuming. And if I substitute, we know the delta I equal to Vs into K 1 minus K upon FL. If I substitute delta I equal to 2 times IL, I should be getting this as equal to 2 into IL. I'll take it equal to IA. That is equal to, substituting that, I'll be getting 2 into IA. What is IA? IA is nothing but voltage by resistance. So output voltage is K into Vs upon R. Okay. So next, this gives a critical value of the inductor LC. So LCI is equal to L equal to take L on the left hand side. So I'll be getting this Vs cancels. So it will be 1 minus K. K also gets cancelled. 1 minus K upon F 2F. This 2 comes below 2F into R. So this is an equation of the inductor L, which we call it as the critical value. Hence I'll name it as LC. Similarly, if Vc is the average voltage, now this is the voltage across the capacitor. So if Vc is the average capacitor voltage, the capacitor ripple current delta Vc will be 2 times Va, right? 2 times, this is Va, so 2 times Va. So using this equation, I will substitute. We know delta Vc equal to Vs into K1 minus K upon 8 LCF squared. I will substitute this as 2 times Va, which is equal to Va we know equal to K into Vs. So the critical value of capacitor now can be found as Cc is equal to, take C on the left hand side, and this you bring down, so K and K cancels, Vs cancels. So 8 into 2 becomes 16 LCF squared. Okay, so this will be the two value path. So now we have just done the summary of continuous current case. The critical value of the inductor is LC equal to L equal to 1 minus K into R upon 2F. The critical value of the capacitor is Cc equal to C, which is equal to 1 minus K upon 16 LF squared. So these are the derivations of the capacitor and the inductor. So the condition for continuous inductor current and capacitor voltage, we are talking about continuous. The buck regulator requires only one transistor and is simple and has a high efficiency greater than 90%. The di by dt of the load current is limited by the inductor L. However, the input current is discontinuous and a smoothing input filter is normally required. It provides one polarity of output voltage and unidirectional output current. So it's a first quadrant operation. It requires a protection circuit in case of possible short circuit across the diode that we have done. Now let us look at an example and find the values of LC filter for the buck regulator. So this is the typical circuit diagram for a buck regulator. Okay, since we are incorporating feedback and we are going to give pulse width modulation here, this becomes the buck regulator using the switch mode power supply. Switch mode regulator. Okay. Now the buck regulator here has an input voltage here Vs equal to 12 volts. The required average output voltage is 5 volts and the resistance of the load is given as 500. And the peak to peak ripple voltage, okay, is given as 20 millivolts. So delta V is also given. The switching frequency is 25 kilohertz, so F is 25. If the peak to peak ripple current of the inductor delta L is 0.8 amperes, determine the duty cycle K, the filter inductance L, and the capacitor value C, and also the critical values of L and C. Now looking at the parameters that are given to us, Vs is 12 volts, delta Vc is 20 millivolts, delta I is 8.8 amperes, frequency is 25 kilohertz, and output voltage Va is 5 volts. Now in the first part of the problem, we have to find the duty cycle. So we will take output voltage equal to a duty cycle into the input, that is Vs. So from this I get K equal to Va upon Vs, that is output voltage is 5 divided by 12 input voltage. That gives me 0.4167, that is 41.67%. In the part B, we have to find the value of L. For that, I'm using this formula. Delta I is equal to Va into Vs minus Va upon Fl into Vs. So taking L on the left hand side, I will substitute Va is 5, Vs is 12 minus 5 upon 0.8 is delta I comes down, which is equal to 0.8 into F is 25 kilohertz into 12. So this will solve and we'll get 145.83 microhenries. To calculate the value of C, I will be using delta Vc equal to Va into Vs minus Va upon 8 LCF squared into Vs. Now note that delta IL has almost the same formula as this. So I can substitute VA VS minus VA upon F into L into Vs as delta I itself. Okay. So what is remaining will be this 8 into delta Vc will come down into F is what is going to remain. Rest all will remain same. So delta I, I'll put it as 0.8 divided by 8 into delta Vc. Delta Vc is given as 20 millivolts into F, that is 25,000. So this will give me SE value as 200 microfarads. To evaluate the critical value of inductor, LC equal to 1 minus K into R upon 2F. This is the formula used. Substitute all the known values here and I should be getting the critical value as 5.83 millihenries. And the critical value of the capacitor can be evaluated using this formula, that is 1 minus K upon 16 LF squared. Substitute all the known values now here and you should get the critical value as 0.4 microfarads. So with this, we'll move on to solve this. So the summary is, we have basically dealt with today in this video the buck regulator. We have understood switching mode regulators and the buck regulator in particular. We have also understood what are the waveforms and the derivations for continuous current. Okay, and we have seen the example problem with respect to the buck regulator.
So I thank you, dear students, for this patient listening. And if you have any doubts, do get back to me. Thank you so much.